All right, this presentation is building upon some stuff we talked about in class. I'm going to go through, first of all, approaching a problem where you're not given any numbers, but you're simply given variables. So the setup that I have here is that a projectile is launched with an initial velocity of VO at an angle of theta in such a manner that the starting height of the projectile is going to be equal to the landing height of the projectile. And the question is, how far downrange will this ball projectile land in terms of VO, theta, and G? So if you were to see a problem like this in our class or on the AP exam, you simply are solving for the answer, and your answer can only have these variables in it at the very end. Now, I've also included G here. Technically, G is not a variable, it's a constant, but I just want to make sure everyone understands that it can be a part of this. The other thing that I'll say right now, and we'll see a little bit more clearly later, is the fact that your answer can have mathematical functions in it. So addition, subtraction, multiplication, division. This particular answer will end up having a trigonometric function, specifically the sine function. So don't be too worried if you see something like this. You might be slightly uncomfortable with it now, but you're going to get better at it. The other thing that I'm going to say right now is this one works particularly well with the material we're doing right now, but there is some stuff in it that you would not be expected to do for an AP exam. So I'll point that stuff out later. So this itself would not be an appropriate AP exam question, but the style of the question is, I think, what we're getting at here. And we are going to do practice with this later this week. So let's take a look at what we have. We're going to organize our information next. So if I go down, I've broken stuff up into the x-axis and the y-axis. In this case, it makes the most sense to call x initial 0 meters, y initial 0 meters, and then because y final is the same as y initial, y final is also going to be 0 meters. This being a projectile problem, keep in mind that I've left out acceleration because I'm going to use our acceleration formulas where I already am using acceleration on the x as 0 meters per second squared and acceleration on the y as negative g. I've also put the time in between both the x and y axis because that is shared between both of them. The next thing we're going to do is we're going to approach this very similarly to the example problems that we've done in class already. So when we did these in class, the first thing we had to do was take a look at the initial velocities. So over here I have initial velocity on the x-axis on the left, the little x there, just so we remember, and we have initial velocity on the y-axis. What I'm getting at here is you can't just take this initial velocity and say, oh, that's VOX, or oh, that's VOY, because that initial velocity is at a diagonal. It's in between both our x and y axis. So what we're going to have to do here is we're going to break up that initial velocity into its component vectors. Now, you might be sitting here going, well, yeah, but I don't have numbers. That's okay. We're just going to do the algebra for it. And I know some of you might right now be going, but can't we please use numbers? And the answer is no, we're not going to use numbers because you got to use to this. All right, so follow along with me. What I'm going to do, clean this up a little bit, is break into our component vectors. So I want to come out here. And let's do it in a different color just to make it look pretty. And I'm going to clean this up a little bit because I don't like bad vectors. All right, so if we were going to do this with trigonometry, we would say, all right, this here is Vox, and this is Voy. And if I wanted to solve for Vox, I would be using a cosine function. So we're saying that the hypotenuse is VO, our angle is theta, and this is the side that is adjacent to the angle. So I'm now going to write cosine of our angle is equal to the adjacent side, Vox, over the hypotenuse, which is the overall initial velocity. And if I want to solve for Vox, I'm going to say that Vox would be equal to VO cosine theta. Now I'll quickly point out this is good because now we have Vox, and what we would say is in terms of VO and theta. Let's reiterate here. I am saying that Vox and this are the same thing. What is on the right is Vox. But instead of saying Vox, I have it on the right in terms of VO and theta. Okay? So that's an idea that you need to start to think about and understand. Okay? All right. On the other side, VOY is the opposite of the angle. We have our hypotenuse and we have our angle, so this time I'm going to use a sine function. So I'm going to say the sine of theta is equal to the opposite side, VOY, over the hypotenuse, which is VO. I'm going to solve for VOY, and now I know that VOY is equal to VO sine theta. I now have VOY in terms of VO and theta, which are variables I'm allowed to use according to this. All right? Just to wrap things up and make things fully straightforward, hopefully, let's just do the I hat, J hat notation for our VO now. So what I'm saying is that VO is equal to VO cosine theta I hat plus positive, it's going up, VO sine theta J hat. All right? So now, if I take this information I can add it to what we know. So let's just highlight that we figured that out. So the other thing I'm going to point out here now is when we've done problems with numbers, this is essentially what we did. We took the sine of an angle and the cosine of the angle, and we solved for what the opposite side of the initial velocity components were, and we solved for the adjacent side for those vector components of the initial velocity. So we just ended up with numbers in the past. Okay, so nothing different here. We just don't have actual numbers to look at. Now, just like other problems we've done, what we're looking for is this value here. So when we say how far downrange, we're saying that x is equal to the range, and that's what we want to figure out. And this is where you might say, okay, well, what do I have? Do I have enough information on the x-axis? I have x initial, I have VOX. The formula that I want to use for the x-axis is going to be x final equals x initial plus VOXT. And the issue is, this is the only x-axis formula for projectile because there's no acceleration on the x-axis for a projectile, and I don't have the time. So just like we've done in the past, if I don't have the time for the x-axis, I'm going to come over to the y-axis to solve for time because the time is the same for both of them. All right, so when I go over to the y-axis, I see I have y initial, y final, VOY. What formula can I use to solve for time that doesn't require me to know my final velocity? Well, just like in the past, we are going to use y final equals y initial plus VOYT minus 1/2 GT squared. We say, in this case, from our given information, y final is 0, y initial is 0, and make those zeros. Now we have 0 equals VOYT. Well, I know that VOY is VO sine of theta multiplied by t minus 1/2 GT squared. And by the way, I'm specifically leaving out I'm not going to enter in 9.8 for G right now because things are going to work out nicely for me later. So no need to start plugging numbers in if I don't need to here. All right, so how would I solve this in math class? I would factor out a t. Remember, t is what we're looking for this particular formula. So I've got t, is VO sine theta minus 1/2 GT. Okay, so basically our unknowns are t, and our knowns here, the variables we're allowed to work with are VO, theta, and G. So I'm really in good shape. I just need to get t in terms of VO, theta, and G. All right. So doing your math here, what we're saying is that this term multiplied by this term will give me 0. So one option is that t equals 0. Great. All that's saying is that time equals 0, the height of the ball is 0 on the y-axis. True statement, not useful to me. The other thing that I could do is get this term to be equal to 0. So then I would be multiplying this term, 0, multiplied by whatever t is, and get 0 as an answer. So I'm going to say this could be equal to 0, but for that to be true, we'd have to say 0 equals VO sine theta minus 1/2 GT. So what would t have to be in order to get this to be 0? Well, solve for t. So let's do that down here. and I get 1/2 GT, bring that to the other side, is equal to VO sine theta. And I'm going to multiply both sides by 2. And then divide both sides by G. And I get that T would have to be equal to 2 VO sine theta over G. Now once again, this is looking kind of messy, but I'm just going through the process that we've gone through a number of times before with our example problems in class. We solve for the x-axis and y-axis components of velocity, and now we're solving for the time using the y-axis. It looks messy because it's algebra, but it's still the same idea. All right, now we're going to take this time that we've calculated. Even though we don't have a number, we now have the time. We just have it in terms of VO, theta, and G. So that comes back up here. Oop, there we go. And we've now figured this out. And we have enough information to solve for the range now. It's just going to be an algebra equation, okay? So here we go. This is the formula we want to use. Give us a little bit more space to work here. So we're going to say the range is what I want, is equal to XO, which we know is 0, plus VOX, and I already know that VOX is equal to VO cosine theta. So that's in terms of VO and theta now. Our time from above is this guy here. And you might go, oh, that looks awful. It is a little messy algebra. Okay, but what I'm going to do is going to say, okay, let's start putting things together. And so now I have range is equal to 2, or actually I'm going to do this, VO squared over G. And you can take a look at that. Am I doing legal algebra? Sure. I'm putting VOs together, and I've got it divided by G. Everything else is being multiplied, so I'm following my order of operations rules. And I end up with this. 2 times the sine of theta multiplied by the cosine of theta. And you might say, that looks ugly. And it does. And this would actually be an acceptable answer now because we have everything in terms of VOG and theta. See? Look at this. I only have a VO, a G, and thetas. You know, I do have trig functions, but those aren't variables. They're just functions. I have multiplication. I have division. So this is actually answering the question. But I'm going to take it one step further. I'm going to do something that you probably don't know. I'm going to take this and I'm going to apply what's called a trig identity. Some of you may have learned some of these already in math class, and many of you may not have. That's okay. You're not expected to know this for this class, but I'm going to use it because it's going to make a nice looking formula for us. So it turns out that this is also equal to the sine of 2 times the angle. They're equivalent to each other. And so now I can take this formula and I can make it look a little nicer by using this instead of 2 sine theta. So let's rewrite that. I now have something that says the range of a projectile, and don't forget our definition of range. Range is the horizontal distance that the projectile travels when initial height equals final height. Multiplied by sine of 2 theta, and there you go. You get a nice little equation. This equation is actually referred to as the range equation in physics. And if you have a range situation, you are welcome to use this formula. I will give it to you as an additional formula for you to use on the test. But remember, only can be used for range. And that's when y initial is equal to y final. If that's not the situation, don't use this formula, because if you do use it in a situation where y initial doesn't equal y final, I will have to write on your test, bad, and we don't want that. All right, so now you know the range equation. We have a lab that we've done based on this, and hopefully you're starting to get some idea of how this is going to apply, but you will need this formula for the what goes up must come down lab. All right, enough talking from me. I will see you in class.